So we've practiced using Beer's law in chapter 18. The, absorbance equals the extinction coefficient times the path length times the concentration. And that works great when we're measuring one compound because the concentration of that compound is directly proportional to its absorbance. So using this equation, we can measure the absorbance using a spectrophotometer and then calculate its concentration as long as we figured out the extinction coefficient. But the world is usually a little bit more complicated than this, especially if we have things that we're testing that are unknowns. So in the lab, often you're handed a pure chemical and, make the standards and then here's the unknown, which only has one active ingredient in it, test that. But in real life, if we're testing like a pharmaceutical drug and we're trying to measure the concentration of one of the compounds in the in the pharmaceutical drug, that pharmaceutical drug is actually a mixture. There's going to be multiple things in there. And often there will be another compound that also absorbs light at whatever wavelength that the active ingredient, the chemical that we're testing, absorbs light. And so we have to learn how to handle, if we've got a mixture and multiple things in that mixture absorb light at the same wavelength, how do we handle those calculations? Because in that situation, the absorbance will be higher than it would be if just the one compound was there. And so this equation would be like the total concentration, right? It wouldn't give us the concentration of just one compound, but what we want is the concentration of each individual compound. So we're going to do an example for how to apply Beer's law to a mixture. So we can say that absorbance is additive. So like I said before, the total absorbance would give us the total concentration. So what we're going to need to do is to test to test our samples at two different wavelengths. So maybe we have two compounds, both of which absorb light at the wavelength that is the lambda max, the ideal wavelength, for one compound. Now the other compound, that's probably not its lambda max. It just happens to absorb some light at that time. So we're going to need to measure these mixture solutions at both wavelengths, the lambda max for compound 1 and the lambda max for compound 2. Now we know that the absorbance that we will get in both situations will be the total absorbance. So we're going to have to break that down more. So this is the version of Beer's law we'll be using with a mixture. And all that it is saying, well, hey, they add together. So X is like the first compound, like compound 1, compound X. And then the Y is like the second compound, compound Y. Each of these are just Beer's law. The path length would be, well, I'm going to go with 1.00 centimeters because that's what our cuvette sizes are, but they would be consistent for both of them because they would be in the same cuvette. So that's why the B doesn't have a subscript of X or Y. So we would do this and measure the total absorbance at lambda max 1, and then do it again for lambda max 2. And then compare those. So we're going to have two equations. Now we would obviously have to have the extinction coefficient at lambda max 1, and then we'd have to have it again. So at lambda max 2, we have the same equation. Sorry. There we go. And so their extinction coefficients are actually going to be different at each wavelength because the chemicals absorb light differently at different wavelengths. So we're going to have to solve for 4 extinction coefficients. The extinction coefficient of compound 1 at the first wavelength and compound 2 at the first wavelength. The extinction coefficient of compound 1 and compound 2 at the second wavelength. And then we can use these two equations to solve for the concentrations that we're looking for, because the concentrations will be the same in both situations. Oops, I don't know what that just did, but ooh, zoomed in. Okay, undo. I'm going to change colors here. So the concentrations, CX and CX, those will be equal. CY and CY, those will be equal because we have the same amount of chemical both times we test it. All right, so there we go. There's our absorbance 1 and absorbance 2. We're coming from wavelength 1 and wavelength 2. So this is what a picture would look like if we were to take that mixture and instead of just measuring the absorbance at one wavelength, but show the spectrum of multiple wavelengths. So we looked at these before when we were determining what the lambda max was. The lambda max is the wavelength that we choose to measure for a compound. So for like compound X, it would be whatever, it's the top of the hill. So whatever that wavelength is would be the lambda max for X. And for compound Y, we'd have to choose either here or here. I would probably go with here. That would be the lambda max for Y. And so in the top box, the blue curve was just compound 1. That was the only chemical in that solution. This was not a mixture. And the black curve is just compound 2. So again, not a mixture. Down here, we can see kind of what it looks like once we have our mixture, and see that at, like, for example, at this wavelength, there's going to be an absorbance coming from that compound and an absorbance coming from this compound. Now, of course, this compound, it's not absorbing as much, but the instrument would measure both total. Okay. So what kind of happens is we see this overlap. We see all the hills show up in the mixture. Okay. So there's that hill, again, showing the mixture. So we would have to decide which wavelengths that we would, so that's like lambda max 1 and lambda max 2. So let's try one of these. Now the question's super long, so I'm going to obviously have to go to the next slide to do the math. So I am just going to assume that the information we have here, that we remember it going forward. So this one, we've got a mixture of potassium dichromate and potassium permanganate. And they have overlapping absorption spectra, and they're in a 1 molarity sulfuric acid solution to keep them stable. So potassium dichromate has a lambda max absorption maximum of 440 nanometers, and potassium permanganate has a lambda max of 545 nanometers. So I'm telling you, we're going to test it at 440 nanometers and at 545 nanometers. We tested it, and this is what we got. The absorbance at 440 nanometers was 0.405, and at 545 nanometers was 0.712, and we have a 1 centimeter cell, so that means B. I know it just says 1, but I'm going to go ahead and 1.00 centimeters. So there we have that. And then the absorbances of a pure solution of potassium dichromate and then a pure solution of potassium permanganate with their molarities given, using the same cell, which means it's also a path length of 1, we got these absorbances. So this first sentence up here that I just put in parentheses, that's for the mixture when they were poured in the same solution, the same, flask. And then this bottom one, I guess I should change colors. Going from there to there, were for 2 different solutions that are pure. So a solution that just had potassium dichromate and sulfuric acid in it, probably, and then one that had potassium permanganate and sulfuric acid in it, and we got these results. So what's going to happen is the second sentence that I put the purple around, we were given a molarity and we were given absorbances, so we're going to have to use those to solve for the extinction coefficients at each of these 4 scenarios. So again, when we have a mixture, we're going to measure the absorbance at 2 wavelengths. And so what they did here was they measured the absorbance of the potassium dichromate solution at 440 and at 545. And then they measured the absorbance of the permanganate solution at 440 and at 545. And so we're going to have to solve for the extinction coefficients of both of those. So that's what we're going to start with, is actually using the second sentence first. So instead of writing dichromate, I'm just going to write chromium. I'm being lazy. Okay, so we're going to look at the information about chromium at 440 with the pure standard. So we were told that the absorbance was 0.374. That's coming from the last slide. We do not know the extinction coefficient of chromium at 440 nanometers. We don't know that, but we know that B is 1.00 centimeters, and C was given in the problem also as 1.00 times 10 to the negative 3rd molarity. So I can just use algebra here to solve for the extinction coefficient, and I got 374, and its units will be inverse centimeters, inverse molarity. Now I'm going to do it for chromium. We were also told that it was tested at 545 nanometers, so I'm just going to take the data values that we were given there, plug them in, do the same thing. Still 1.00 centimeters. So for this entire problem, the path length is 1.00 centimeters. And then we solve for the extinction coefficient of chromium at 545. We get 9, and the unit is inverse molarity, or sorry, inverse centimeter, inverse molarity. So that was for the chromium standards. Now I'm going to change it for the manganese. So for manganese at 440, the absorbance we were given was 0.019. Manganese at 440, 1.00 centimeters. And then the molarity of the potassium permanganate was given to us as 2.00 times 10 to the negative fourth. Oops. So the extinction coefficient of manganese at 440 nanometers, when I did this math, I got 95. Inverse centimeters, inverse molarity. So what I'm going to do, I ran out of space there. I'm going to come over to the other side, and we're going to do manganese at 545 nanometers. So its absorbance was 0.475. We don't know the extinction coefficient. I can fit this, can't I? Sure. There. And then 2.00 times 10 to the negative fourth molarity. There we go. The extinction coefficient of manganese at 545 was, I put this in scientific notation, 2.38 times 10 to the third inverse molar, or inverse centimeters, inverse molarity. So the purpose of this was, before we use the equations that were shown earlier in the slides, we need to know the extinction coefficients. So instead of being given the extinction coefficients in this question, I gave you the information needed for you to calculate them. Okay. Now, a question like this, I could have just, instead of giving you, here's the absorbance, here's the molarity, I could have said, hey, here's the extinction coefficient. So you could have been given this information and been able to skip this step. But since these solutions, I'm going to backtrack here, these were pure solutions, you can just use the regular old school Beer's law, and that's what we did. Okay, so now we got the information we need. We're ready to tackle the mixture. Okay, so when we look at the mixture, we're going to have to use, I'm going to go to another slide here, the big equation, which is the absorbance total is equal to the extinction coefficient of chromium at 440 times B times the concentration of chromium plus the extinction coefficient of permanganate at 440 times B times the concentration of manganese. So we have 4 extinction coefficients from the last slide, one for each chemical at each wavelength. So that's why I have both the chemical and the wavelength listed there. So we're able to plug in lots of numbers for this. So for the absorbance, I'm going to plug in, I guess I'll do it, I'm going to scoot it over here because these numbers are going to be long, 0.405. The extinction coefficient was 374 inverse centimeters, inverse molarity. The path length is 1.00 centimeters. The concentration of chromium is unknown. If you don't like this, you could just write X there as an unknown. That's fine. And then the extinction coefficient of the permanganate from the last slide was 95. And if you wanted to, you could make that like Y or something. Okay. So what we're going to do here is do the same thing, but at 545 nanometers. So we're going to have to look at the extinction coefficients and the absorbances that were given at 545. So for this, we were given 0.712, and the extinction coefficient of chromium at 545 was 9. Concentration of chromium, and the extinction coefficient for permanganate was the 2.38 times 10 to the third. Centimeters inverse, molarity inverse, 1.00 centimeters, concentration of manganese. Okay, so what we need to do is we have to use these two equations to solve for the concentration of chromium and the concentration of manganese. I have 2 unknowns and I have 2 equations. So what we're going to do is substitution. So we have to decide which equation we want to use to rearrange the equation so that way it's equal to one of the variables. So I'm going to choose to take my first equation, this one, and I'm going to rearrange it to solve for the concentration of chromium. So that equation, I'm going to draw a line down here, and what I'm going to do is concentration of chromium equals And then it's going to be 0.405 minus 95. I'm going to be lazy here, and I'm going to drop the units. So I took this equation up here, and I just rearranged it to get chromium by the concentration of chromium by itself. So I subtracted 95, and I also multiplied through, like the 1 centimeters are gone, I multiplied them. So subtracted by 95 concentration of manganese, and then I divide by 374 to get here. So then I'm going to take this, and I'm going to substitute that into equation number 2 to try to make it so I only have one variable. So I'm going to take equation number 2. And instead of concentration of chromium, I'm going to put in this. Plus 2.38 times 10 to the third times the concentration of manganese. So what we have is this variable and this variable are the same. So we have to do some algebra here. We need to simplify this whole mess and then combine like terms. Get all the concentration of manganese on one side and the ones that don't have a variable on them on the other side to solve for this. So I'm gonna kind of skip some of that algebra step and say I'm skipping a couple steps. This was me, doing the algebra and then combining like terms. So I need to divide both sides by, it looks like 2,377.71. So I got the concentration of manganese to be equal to 2.95 times 10 to the negative fourth molarity, or we could write 0.000295 molarity. That gives me the concentration of manganese. Oops. Yep, just dropped the cup. Everyone's fine. Everything's fine. Okay. So that's awesome. I've got one of the concentrations, but what I need is the other concentration. So what I'm going to do now is just take this number and substitute it into any of the equations that I've written up here to solve for the concentration of chromium. So we could do that literally with any of them. So we could take this equation right here and substitute that in for the concentration of manganese. It really doesn't matter to solve for the concentration of chromium. When I did that, I have 9.94 times 10 to the negative third, negative 4 molarity, which is 0.000994 molarity. That let me solve for the concentration of both chemicals in the mixture. It took a little bit longer because my Beer's law calculation was not as straightforward because I had these two longer equations and then I had to do substitution. But I would definitely be prepared to handle a question like this on the exam. I'm pretty much promising you I'm going to give you one of those. Whether you have to do this work to solve for the extinction coefficients on your own or whether or not in the question I would have given you the extinction coefficients, it could go either way. But that's how you're going to handle mixtures calculations when we're dealing with absorbance.